Let's talk about graph theory, vocab, and definitions. So a graph is a collection of vertices, which are often just shown as points or dots, and edges, which are often lines or sometimes curves, that represent any connections between the vertices. In a connected graph, each vertex is connected to each other, even if the connection isn't direct. So if I draw something like this, all of these vertices are connected to each other because by following edges I can get from any one vertex to another. Compare that with a disconnected graph, which is one or more isolated vertices. So if I draw the same 6 dots, in a graph like this is an isolated vertex. And this graph would be said to have 2 components because one is made up of these 5 that are all connected to each other, and the other component would be made up of this isolated vertex. A loop in a graph connects a vertex to itself. So if I draw something like this vertex down here would be said to have a loop because there's a path that goes around and reconnects to the exact same vertex. Vertices with multiple edges have more than one connection or edge between them. So if I just draw this same picture, these 2 vertices have multiple edges because there's more than one path or edge that connects them like this. We say vertices are adjacent if they are connected by an edge. So if you draw a picture like this, these 2 are adjacent because there's one edge that connects them, but these 2 are not adjacent because they are connected, but it takes 2 steps to get there, so they are not adjacent. The degree of a vertex is the number of edges that start or end at it. And a simple way to go about this is just to write in the number of connections at each vertex. This one only has 1. This one has 1, 2, 3, 1, 2, 3, 4, 1, 2, just 1, and 1, 2, 3 again, just like that. The degree sum of a graph is the sum of degrees of each vertex. So if I draw that same picture again, the degree sum is 14, which I get just by adding all of these up. A simple graph has no loops or multiple edges, so this is a simple graph. There are no multiple edges or loops. This is not a simple graph, though, because it has a loop down here, and there are multiple edges that connect these 2 vertices. A path is a route from one vertex to another that uses edges exactly once. It doesn't have to use every edge, but it can't use any edge more than once. So something like ABC is a path, but ABCB is not a path because I would have to use this edge twice. A circuit is a path that starts and ends at the same vertex. Using this picture here, ABCDEA is a circuit, ABCDEA. It's a path because I haven't used any edge more than once, and it starts and ends at the same vertex. If I do this misformed star in the middle, you get ACEBDA is another circuit. A special kind of path is called an Euler path. It's a path that uses every edge in the graph exactly once. In this graph, if I go A, B, C, F, E, D, A, F, you could count off that I have used every edge exactly once. It's a path, but it uses every edge, but I have not come around to where I'm starting. If I use every edge in the graph exactly once and I return to where I started, that is an Euler circuit. In this graph, I've drawn it poorly, but there are supposed to be multiple edges between B and G. So if I go A, G, B, F, C, D, E, C, G, B along the other edge of the multiple edges and back to A, I have an Euler circuit. Lastly, I want to talk about isomorphic graphs. These have the same adjacency structure. Well, that is kind of a mouthful. To see what that means, let's just draw a few graphs. Here I've drawn 6 graphs, each of which has 5 vertices. To determine which ones are isomorphic, it helps to label the degrees of the vertices. Now the way to think about isomorphism is, could you just move these dots around but keep all the edges intact so that make one of them look like the other one? And that can be very difficult to picture, especially if there's a lot going on. So just look at which vertices have what degree and what they're attached to. For example, in these two, there's a 1 here and a 1 here, but this one has 4 and this one has 3. 1, 4 and 1, 3 means these two cannot be isomorphic. The only other one that has 1 is over here. The 1 is connected to a 4, which is the case here too. The 4 is connected to a 2, and a 3. This 4 is connected to a 2, and a 3. And you might be able to picture, if you're good at visualizing these things, that if you just kind of rotated this around and rotated this up and rearranged these, that these two would be isomorphic. So let's look at the other ones. This one is a 4, 2, 2, 2, 2. None of the others have a 4 with 4 2s. These two look like maybe they are because there's 2 3s and 3 2s. 3, 3, 2, 2, 2. And here you have the same thing, 3, 3, 2, 2, 2. But what you notice on this one is that the 3s here are adjacent to each other. These 3s are connected by an edge. But here the 3s are kind of all on their own. The 3s are not adjacent to each other, so D and F are not isomorphic. And that is what we mean here. The same adjacency structure means the structure of the graph has to be the same with the same number of vertices, same number of degree each, but the adjacency also has to be the same. In these two, the 3s have an edge between them, but in here, the 3s are not adjacent, so they are not isomorphic. These are the only two isomorphic graphs that I've drawn.